Let's work out an example of finding the center of mass of an object. Suppose that we're interested in finding the following. Find the centroid for the region that is between f of x equals natural log of x equals 1, x equals 2, and y equals 0. In other words, the region we're looking at is the one that is between the function f of x equals natural log of x, the line x equals 1, the line x equals 2, and then the horizontal axis. That means this is the shape we're talking about. In other words, to find the centroid for this, what we need to do is we need to compute the x moment, the y moment, and the total mass. In this case, since we are just interested in finding the coordinates of the center of mass that are basically given by these equations, we don't need to know what is the density for this shape. If we were just looking for moments, then we would need to know what is the density. But in this case, we can just assume density to be a variable called rho, but we don't need to know the numerical value for rho. So for the moment, what we're going to do is we're going to find out what are the moments and then find the coordinates. In other words, we have that the x moment, the equation for x moment is going to be our density, which in the end is going to cancel out. Then we have the integral between a and b of f of x squared divided by 2 dx. This is the general formula that we have for x moment. So in our case, we have that this turns out being rho, the integral between 1 and 2 of natural log squared divided by 2 dx. In other words, we can write it down as rho over 2, the integral between 1 and 2 of the natural log squared dx. So in order to work with this integral, we can use a u substitution. So we can set u equals natural log of x. Then that gives us that du equals 1 over x dx. And we have that x is from our substitution is the same thing as e to the u. In other words, we have e to the u equals x. So that means that du equals 1 over e to the u dx. So this substitution makes us write the original integral as rho over 2, the integral of u squared, and then dx is actually e to the u du. Now this is a more familiar integral. This will actually be an integration by parts, and we know because of the exponent of this that we would need to do that twice. So now we know what to do. The only thing that we are left with is to carry the bounds of integration. That means if x equals 1 and if x equals 2, what are the corresponding values for u? So we have if x equals 1, then u equals 0. And if x equals 2, then u is the natural log of 2. So this becomes the integral between 0 and the natural log of 2. That means that now we have to use integration by parts twice. So that is exactly what we're going to do. I'm going to take the u part, which I'm going to call v or w to make it less confusing, to be this part, and then dv is going to be the rest. In other words, we have that w equals u squared, then the dv equals e to the u du, which brings us to w being 2u du, and v to be the same expression, e to the u. So this gives me that the original integral is going to be rho over 2, and then we have our integration by parts formula. So that would be the product of these two, which is u squared e to the u, minus the integral of these two right here, which will give us 2u e to the u du. And the bounds of integration remain the same. So notice that by applying the integration by parts once, we were able to reduce from a quadratic to a linear. So we can repeat the process again. Now the substitution that we are going to do is w equals u, and dv, the same thing, e to the u du. So we have dw equals du, and we have v to be e to the u. So again, we're doing this strategy basically. So this one gives us that the original integral is rho over 2. We keep the u squared e to the u minus 2 times, and now this is where we apply the new integration by parts. This will become u to the times e to the u minus the integral of just e to the u du. We keep the same limits, and then this is the last expression we have. In other words, this will make our original integral to be rho over 2. Then we would have u squared e to the u minus 2 times u e to the u minus e to the u, and everything in between 0 and the natural log of 2. So now we just have to evaluate the top and the bottom, and that will give us our first moment. So this will be rho over 2, and then everything at natural log of 2. So this will give us the natural log of 2 squared times e to the natural log, which simply is going to be 2, minus 2 times the natural log of 2, and again e to the natural log, that is just going to give us 2, minus e to the natural log, which is just a single 2, and then everything at 0, and everything at 0 will be, the first part will be 0, second part will be 0, and then we only have a contribution from the very last one, so this will be minus 1, and that's the only one that it's coming from 0. So if we simplify this a little bit, just to make it a little bit nicer, we will have rho over 2, and this becomes 2 times the natural log of 2 squared minus 4 times the natural log of 2 minus 2, and then this becomes a plus 1, so this becomes minus 1 in the end. So that will be our first moment. This is the x moment. That's the very first one that we have up here. Now we have to do something similar for the y moment. So we're just halfway through. Now we have to do the y moment, which is rho integral between a and b, and now we have x fx dx. So that's always the expression that we have for the y moment. In our case, this should be rho integral between 1 and 2, x natural log of x dx. So we should think about this as another integration by parts problem. We can take this one to be our dv part, and this one to be our u part, because we want to take the derivative of natural log. In other words, we can set u to be equal to natural log of x, and we can set dv to be x dx. This gives us that du is 1 over x dx, and v will be x squared divided by 2. So again, we do the same thing as before. We do uv minus v du. So this will give us rho, and then applying the integration by parts will give us x squared divided by 2 times the natural log of x minus the integral of just 1/2 x dx. So this one actually is a lot better than the previous one, and we keep our same bounds. In other words, this becomes rho times x squared natural log of x divided by 2 minus 1/2 the integral of x, which is x squared divided by 2, and everything between 1 and 2. So we can plug everything at the top and everything at the bottom, and then we have rho times everything at 2, which will give us 4 natural log of 2 divided by 2 minus 1/4 2 squared, which is 4, minus everything at 1, and that will be 1 times the natural log of 1, which is 0, and then the only survivor will be 1/4 1 squared. So if we simplify this a little bit, we have rho, and then we would end up with 2 times the natural log of 2 minus 1 plus 1/4, so that would be minus 3/4. Now we have our x and y moment. The only thing that we're missing is to find out what is the original area. In other words, we need to find the original mass, the total mass of everything, which is just the integral, rho times the integral of AB f x dx. And in our case, that will be rho, the integral between 1 and 2 of the natural log of x dx. Now, the good thing about this is that we have the integral of the natural log. That's one of our common integrals. So that if we don't know it, we can work it out with integration by parts. But it's a common thing to remember that this is just going to be x natural log of x minus x between 1 and 2. So again, even if you don't remember what is this part, you can find it out by using integration by parts once more. So now we have to plug everything at the top and everything at the bottom. So this will become 2 times the natural log of 2 minus 2. That's everything at 2. Minus everything at 1. We would have 1 times the natural log of 1, which is 0. So the only survivor is a -1 in here. So in the end, this is just rho times 2 times the natural log of 2, and then we have minus 2 plus 1, that is going to be just a -1. So that's the total mass. Now we have the 3 pieces that we needed. We have our x moment, we have our y moment, and we have our total mass. So we're in good shape to actually compute the coordinates that we need. So we have that the x coordinate is equal to the y moment divided by the mass. So that will give us the y moment that is up here. That's rho. Then we have 2 times natural log of 2 minus 3/4 over the total mass, which is up here, and that is rho. 2 natural log of 2 minus 1. And as we said before, rows cancel, so that doesn't matter. And we have that the x coordinate is just going to be 2 natural log of 2 minus 3/4 divided by 2 natural log of 2 minus 1, which if we compute it numerically, that will be just a little bit under 1. So that's the first coordinate. Then the second coordinate, the y coordinate, that will be our x moment over m. Remember that the moments are flipped, so the y coordinate goes with the x moment and the x coordinate goes with the y moment. So this becomes the x moment, which we have here on top. That is rho over 2. So this will be rho divided by 2. Then multiplied by 2 natural log of 2 squared. So 2 natural log of 2 squared minus 4 times the natural log of 2 minus 1. Minus 4 times the natural log of 2 minus 1. And this divided by the mass that we have here on top. This is rho times 2 times the natural log of 2 minus 1. And again, we have that rows cancel, so this is pretty handy. And in the end, we can have a better expression for this. This will be 2 natural log of 2 squared minus 4 times natural log of 2 minus 1 divided by, so I'm going to divide everything by 2 in here. This becomes 4 natural log of 2 minus 2. So that will be the y coordinate for my center of mass. Again, the only thing that we did was to separate all the three components, the x moment, the y moment, and the mass. We figure out each of these components individually. We used integration by parts several times, which is something that you would expect with this type of problems. And then in the end, we use those two expressions to come up with both of the coordinates.